right. Independence and conditional probability. So this is where I think the probability stuff starts to get kind of fun and interesting. So we'll have a good discussion today, I think. Two events, A and B, are independent if and only if the probability of A and B occurring at the same time is the product of probability of A times the probability of B. Okay. If an experimenter must make a judgment without data about the independence of events, she bases it on her knowledge of the events as discussed in the following example. Answer the following questions in imperative. So I'm going to give you guys 5 problems to work with, and they're going to get increasingly interesting, I think. So consider a single fair die rolled twice. So I just assume 6-sided in all of the problems I give because I guess it's easier. It's fewer words to write. What is the probability that both rolls are a 6? 1 out of 36. But how did you know? Nah! Just you did a lot of trials and it's about 1 out of 36.
When I roll for a full house, what's my odds?
36.
Or a large straight.
2.7%.
So let's do it because it's going to get more complicated in a second. So let's think through it. So let's let event A be that we get a 6. If we assume a fair die, which it was told to us that it was fair, we know that the probability of getting an A is equal to 1 in 6, right? So having no reason to judge otherwise, we assume the results are independent events. Like we don't know anything that tells us that these events are dependent on each other. They're rolling a fair die twice. Probably they're independent as far as we know. So we say that the probability of getting an A or getting a 6 and getting another 6 is the probability of A times the probability of A, which is equal to 1/6 times 1/6 is equal to 1 over 36. Yeah, so that was like stuff that you guys have seen with probability before. Okay, 2. What changes if the die is biased by a weight such that the probability of getting a 6 is 1/7? Yeah, so there is bias, but bias is not dependence, right? So you still have a 1 in 7 chance, but they're independent rolls still. Dependence. Bias is not dependence. So just because it's a biased die does not mean it's dependent. So the probability of A intersect A is equal to, once again, probability of A times the probability of A equals, this time it's 1/7 times 1/7. Okay, cool. 3. What changes if the die is biased by a magnet rolled on a magnetic die rolling tray such that the probability of getting a 6 is 1/7?
It's still the same because probability is still 1 out of 7.
Yeah. So nothing changes, right? Okay. So we're incrementally going to add some stuff. What changes if there are two dice biased by weights such that for the probability of getting a 6 is 1/7 rolled once, both resulting in 6?
Can you say that again?
Okay, what changes if there are two dice? So we had one die before we rolled twice. Now we have two dice, and we're rolling those two dice once.
But the probability is the same since the dice both have
So
the chance of being 1/7.
So still independent, right? So the two rolls still don't depend on each other. Independent. All right, so now what changes if there are two dice biased by magnets such that for each probability of getting a 6 is 1/7, rolled once, both resulting in 6?
So now we're rolling dice individually as opposed to single.
No, we have the two dice together, and there's magnetic bias on each of them. We're rolling them together, two dice on one tray.
So like the dice are connected, so you have like a big dice.
Well, if the probability that it's going to land on 6 is still 1/7, well, would that change at all then?
Their interaction.
They could interact.
Their
for that.
interaction
Oh, so
changes
it's no longer-
statistics.
Now they're not independent.
Depends on where your sixes are. Your
So-
sixes are stuck together.
Right. So you could have a magnetic interaction between the two dice that could, for instance, you could have a magnetic tendency to have them attract, and so a certain face is going to land more often than another. Since when you roll them together, they interact with each other. It made the dice rolling game not completely independent. So we don't know. We don't know what changes because we don't know anything about the magnetic interaction. So they're not totally independent, or they might be, but it depends on how the magnets are set up. We're not clear on it. They could interact, they could influence each other. So we would want to probably investigate that further. You would want to come up with either an a priori reason why a certain result would be more common than another, or you would want to do trials and see if they influence each other. Okay? And of course, this assumes that they're near each other when you roll them. Whatever. If you rolled them far apart, then there shouldn't be any significant interaction. Magnetic fields drop off with like the cube or fourth power of space, so drops off real fast. But so if they're close, though, they can interact. But if they're far away, they're not going to interact. Okay? What do you guys think? Yeah. Potentially dependent. Given what we knew before, on all these other ones, we could judge them to be independent. On this one, we say potentially dependent. We don't know. We would need to investigate further. Okay? So now that's dependence and independence. Conditional probability. If events A and B are somehow dependent, we need a way to compute the probability of B occurring given that A occurs. This is called the conditional probability of B given A and is denoted probability of B, and then this vertical bar here, we read it as given that or such that or something like that. Okay? So the probability of B given that event A occurs, for probability of A greater than 0, it's defined as being, so the probability of B given that A is equal to the probability of both occurring divided by the probability of A. We can interpret this as a restriction of the sample space, omega, to A. In other words, the new sample space, omega prime, is just A, which is a subset of omega. Note that if A and B are independent, we obtain the obvious result. So probability of B, given that A has occurred, is equal to probability of A intersect B, which, if they're independent, is just probability of A times probability of B, right? Based on the last discussion. That was the 1/6 times the 1/6 and the 1/7 times the 1/7. So probability of A times the probability of B, divided by the probability of A. So the probability of A cancels, right? And we're left with the probability of B. So the fact that A occurs has no influence on if B occurs, because they're independent. I mean, that was the whole idea, right? So that should happen. And if we have a formula for which that doesn't happen, that would be a bad sign, right? If we're like, oh yeah, B happening is independent of A happening, then the probability of B, given that A happens, better be just the probability of B happening. Here's a picture that should help with this. Okay? Venn diagram. Pretty nice circles. The first one was a lot better than the second one. I'm going to redo the second one. Better. So, yeah, compass. This is, let's call this A, and let's call this B. So this is A intersect B, right? So what we want to know with these problems is we're saying, okay, we have some information. We know that A occurs. Now we want to know what the probability is that B is going to occur. Pretty much all we're doing here is we're saying, oh, we know that A occurs. So none of this can be the case, right? Only things that are in A can happen now. We've narrowed our possibilities to things that are in A. So here are our possibilities. Oh, look, if you want to know the probability of B given that A, that's just going to be this area, if that's reflective of the total number of possibilities, divided by the full area of A. So we restricted down. Before we could have stuff show up here in B that wasn't in A, but once we restricted it to A, we knew it just had to be inside this A circle. That makes sense? It's kind of like the obvious thing, and I feel like sometimes with this, we make it more complicated than it needs to be. It's really just like, oh, we know some information, let's narrow our problem down. That's really all it comes down to. And it's actually the same. So the next lecture is going to be about Bayes' theorem, and that one's really kind of trippy to people sometimes. But if you draw like Venn diagrams and stuff, and we're going to have like smiley faces and colors, it's a lot better that way. At least in my opinion. All right, so consider two unbiased dice rolled once. Let A be the event that the sum of the faces that are up is equal to 8, and B be the event that the faces are equal to each other. What is the probability the faces are equal given that their sum is 8? Okay, let's do this one. So, any ideas on where to start?
Well, if the faces are equal, I only have 6 options for that.
Yeah, 1, 1.
2, 2, 3, 3, 4, 4, 5, 5, 5, 6, 6.
Mhm.
The sums of the faces, well, we're kind of limited to 6 and 2, 5 and 3, 4 and 4.
It just can't be 1.
Yeah.
Next to the first dice can't be 1.
Yeah, so they have to sum to equal 8. So we can actually, I mean, you can kind of just do this by just like a counting problem, right? Like taking into account all the possibilities. So the probability that you could just like sum up the counting. We could use our, I mean, I would like to use our formula because we have a formula. I like using a formula. Probability of B, which is that the faces are equal, given that A, which is that the sum of the faces is equal to 8, is, according to our formula, just the product. Well, actually, it's not the product. It's the probability of A and B occurring divided by the probability of A occurring. So if you think of it like this, A is sum equals 8, B is faces are equal. And so what we're doing is we're saying, okay, probability of A and B occurring, we got to find this region here. What are the cases where they're both true? The faces are equal and they sum to equal 8. Yes, probability of the event 4 and 4 occurring, right? And then let's sum the other probabilities. So we have the other probabilities are, so at any time the probability, or anytime the event is A, so anytime the sum of the faces is equal to 8, we started listing off possibilities earlier. What are these possibilities? Well, no, they were equal to each other.
2, 6,
2, 6.
3, 5.
Let's also hit 6, 2 while we're here.
6, 2.
Because
Can we just like multiply it by 2 rather than?
okay. All
Sorry,
right.
I'm trying to keep you from having to write it out.
I appreciate it. Yeah. Okay. So then we've got probability of, what was it the next one?
3, 5.
3 and 5, and are there 2 of those?
Yes.
Okay.
And then just 1, 4, 4, 4.
And there's just 1, 4, 4, right? 4, comma 4. And we can't do a 7 and a 1 because you can't get up to 7.
Come on.
I mean, maybe we could bring in a different kind of die, but we don't want to. So, but the probability of all of these events occurring on their own is the same, right?
Why can't we have 2? Why wouldn't 4, 4 occur twice?
It's a good question. So, are those distinct events? Is 4 and a 4 happening? Are there different 4s? If there were 2 different 4s on each die, then that would be distinct events. But a 4 and a 4 occurring when there's only 1 4 on each die there aren't 2 ways that can happen. There's only 1 way that can happen.
Okay.
It is. I agree. There are like philosophical discussions about this. There's a whole thing about it, but it is the case that you should only count an identical event like a 4-4 just one time.
Okay.
So that means that there are this 4-4 happening in the numerator. There's what are the chances of rolling a 4 and a 4?
1 in 36.
Yeah, so it was 1/6 times 1/6, right? We found that in the last example. And then there are 5 of these down here, and they all have the same probability, right? So let's just write 5 times 1/6 times 1/6. And the 1/6 products all cancel, right? And you're just left with 1/5. Yeah. Any questions on that? Pretty fun, huh? Okay.